Pull systems in Kanban. This is a logical follow-on to our previous module on variability and demand variability. And now we're going to talk specifically about how do we satisfy that through the tool called Kanban. If you will, there's a quote, Kanban is like the milkman. Mom didn't give the milkman a schedule. Mom didn't use MRP. She simply put the empties on the front steps and the milkman replenished them. That is the essence of a pull system, from Ernie Smith. So the idea behind Kanban, it's a signal to replenish. It could be an empty container, it could be a card, it could be even an electronic signal. But it's a pull system where the system downstream is signaling upstream that it needs replenishment material, as opposed to this coming from central planning and pushing that process through. So we're going to talk about pull systems in Kanban. Again, it's a follow-on to demand variability. When we talk about pull systems, we're going to discuss that in detail. We'll talk about a pull versus a push system. We'll talk about pull system elements and advantages, and we'll also get into Kanban specifically. Defining pull. Pull is a system of cascading production and delivery instructions from downstream to upstream, and that's the key point. The elements or the operations downstream are signaling upstream that they need replenishment materials, as opposed to a scheduling system that's just pushing things through from centralized planning. I'll continue. From downstream to upstream activities in which nothing is produced by the upstream supplier until the downstream customer signals a need. So in a pull system, that means that no process should produce until the customers have placed orders, whether they're an internal customer or an external customer. And if you look at this particular process, you'll notice that the material is flowing from left to right, Operation A, Operation B, Operation C, yet the information is flowing backwards from E to D, from D to C, from C to B, and so forth. So basically the material is flowing one direction, but the information, that is the signal to produce replenishment material, is flowing backwards, back upstream. A push system, on the other hand, has both the material flow and the information flow going the same direction. This is when a process produces according to a forecast or a schedule. As long as the previous operation supplies the necessary components, they'll keep producing, regardless of what's needed downstream. You can get into a situation where you can just keep piling on additional inventory onto downstream processes, and the signal remains the same. That is, it's coming from outside of that process. So when we look at the difference between the two, a pull system versus a push system, we're also going to talk about one-piece flow versus batch. So I've spent a good bit of time talking about one-piece flow, and we've also talked a bit about batch and queue. Batch and queue is where we have a group of units, 5, 10, 500, whatever that group is, and they go through each step in the process together as a batch. So it may take only 1 minute to process a unit, but if there are 500 in the batch, that unit can't go to the next step in the operation until all 499 of its partners in that group of 500 are complete and ready to move as a batch. So we talk about this system batch and queue because the queue is you have a queue within the process, and when we do batch and queue, we usually have big piles of inventory, multiple batches sitting ahead of each step. The advantage of one-piece flow is that it gives us quicker lead times. That is, there's less time from the time an order is placed to the time it's delivered. It gives us much more flexibility to meet the actual customer demand, drives down inventory, and also drives accountability out of the offices and to where the operators are performing their work. So in this particular example, you'll notice that we have Operation A and Operation B and C and D and E. There are batches of 5 that are going through each process step. Batch of 5 here. Now, it may only take 1 minute to process a particular unit. It goes in, it gets worked on for a minute, and it's finished. However, that group of 5 has to travel together. Thus, it may only take 1 minute to process a unit, but it takes 5 minutes to be able to allow that unit to go to the next step in the operation. So down at the bottom, I've kind of got that outline. The cycle time is 1 minute a unit. There's 5 minutes a batch. There's 5 operations. Therefore, it takes 25 minutes for all 5 units to get through the process and 21 units for the first piece to come through and be ready to go to the next step. Now, this is as opposed, a batch system is as opposed to a one-piece flow. In this case, it's still the same cycle time, 1 unit, 1 minute, 1 unit, 1 minute, 1 unit, and so forth. However, it takes only 5 minutes for a unit to get all the way through the process, assuming no whip in between the stations, and as soon as they're finished, the next one picks it up. And 9 minutes for 5 pieces. So you notice, even though the cycle time required to complete that part was the same, the lead time was dramatically less. So when we talk about push system versus pull system, again, a comparison of those two scenarios we just laid out. The lead time for 1 unit is 21 minutes in a batch operation, yet only 5 minutes in one-piece flow. And the lead time for 5 units is 25 minutes in the batch operation, but only 9 minutes in the one-piece flow. So again, one-piece flow generates a lot of benefits for us, but especially in the lead time and the reduction in inventory. We also get quality improvements and other sorts of, collateral benefits. But for pull systems to be functional, there are several underlying elements that have to be in place. First of all, you have to have reliable processes. That is, the equipment is reliable, it's not going to break down all the time. You can produce your product correctly the first time, that is, it's error-free. And you have good cross-trained personnel that can fill in if somebody's absent or on vacation or gone to a meeting or whatever the case. Second, you have a repeatable process. You have standard work in place, and no matter who you put in that process, they do it in the same way and get the same results. You have a balanced process where you have multiple steps in the process, and as much as possible, they are level loaded. That is to say, each step in the process takes the same amount of time. If in the preceding example we had 1 minute, 5 minutes, 1 minute, 1 minute, 1 minute, you'd have a lot of inventory accumulating before that 5-minute cycle time step, and it would be starving the other steps downstream. So we want a balanced process. And finally, an organized process. 5S is in place. We have the reliable supplier quality and so forth. So we talk about a reliable process. We specifically discuss OEE. We talk about it being error-free. That is, it is not producing a great number of defects. We can trust that the output's going to be usable. And we have cross-trained personnel. Secondly, we talked about a repeatable process where we have standard work. Standards they're developed, they're in place, and we're actually training people according to standard work, and they're following the standard work, and thus we have a repeatable processes. If operators perform their jobs differently every day, the process is likely to vary day to day, and therefore making it very difficult to produce reliable products and make it difficult to plan small production runs. Again, balanced process, level loading. All operators have relatively the same amount of work, and we've got stable scheduling. That is, we're not constantly changing the schedule midstream. We don't issue the schedule if you're going to use the schedule and then change it on a daily basis based on some other reprioritization. That is, we have stable scheduling, and we try to level load coming from our customers, the demand coming from our customers. We try to level load that into the factory, maybe even use a product wheel or some other mechanism. Finally, an organized process is delay-free so that processes can be run parallel in sequence. They begin and they end when planned, and any delays that you have, they would cause increased inventory levels. So, and they move back to the direction of push. So instead, we have managed, reliable processes, and we have reliable supplier quality. So what is a Kanban? A Kanban is just a visual signal to tell you to replenish. It's a transfer of ownership for production from the office to the shop floor. It's a calculated waste. Now, we've talked on this, I touched on this a little bit. Anytime you have inventory, that's a waste in a process. A Kanban system is a planned waste. We know it's a waste. However, we often use the technique or the principle of trading waste for waste. The waste of carrying that inventory is much less than the waste of having a piece of equipment run dry because it has nothing to work on, or starving a customer for what they want, or having long lead time because we've got so much WIP in process. So Kanban, yes, is a calculated waste, but typically in my experience when I've implemented Kanban, we've actually driven inventories down, contrary to what you would think when you think about a Kanban system. That's typically because we have those issues like I explained in the previous module with demand variability, where you have an uncontrolled system, MRP, ordering material because of an imagined consumption, and it just constantly gets put in the mezzanine or on the shelf, and nobody's aware of what's being put on the shelf. So how does a Kanban system work? The most common example is to look at 2 containers or 2 bins. Each container will last you only until the other container can be replenished. So for example, let's say you had 2 bins, and in those bins you had 100 units each. All right. Those 100 units are based on a calculation of what your average consumption is times your lead time, right? Plus some sort of safety stock. So let's say that you use 10 units a week, okay? Or 10 units a day, excuse me. When that, and it's going to take you a week to replenish it. You start working that project, you got 2 full Kanban containers. One container is full, the other container is full. Both of them have 100 units in it. You take that first container and you start working out of it. The first day you use 10, the next day you use 9, the next day you use 11, next day you use 12, next day you use 8, next day. Eventually you get down to where you have 0. We immediately take that empty container, return it to our supplier, and have them replenish those 100 units. Remember, a 1-week lead time. We're relying on that. Once that one container is sent back to the supplier to be replenished, we now switch over our consumption to the second container. So we have an empty space where the first container was, and the second container is being worked out. And we use 12 the first day, and 11 the next day, and 8 the next day, and 10 the next day. About 5 days later, we should be down to 40 or 50 units inside that second container, and the first container arrives replenished, ready to go with 100 fresh units in that we can consume. So we'll keep working out of that second container, 40 and then 30 and then 20 and 10, and finally it runs out. We'll turn it in and get replenished, and we'll immediately switch back to the first container for consumption. So the ideal is that Kanban container arrives at the exact moment the previous one is exhausted. Of course, it's never that precise, but it always should be within your safety stock. We'll talk about the calculations momentarily. There's 2 basic types. In process, that is a visual signal to initiate work within a process, and then material Kanban, it's a visual signal to initiate work between process steps as opposed to within a process step. So an in-process Kanban, in this case, you look and you've got 4 operators working. They're pulling raw material and it goes to operation 1, and then operation 2, operation 3, operation 4, and then it goes into finished goods. The operators only move work when their Kanban is empty, and they can only complete the 1 unit they're working on. They should never have extra units in process. You'll notice that the material is going to flow left to right, and the information is going to flow right to left. So what is the signal for operation 1 to produce? It's an empty spot here. Once they see an empty spot, they will grab a unit, work on it, and produce it to go into that empty spot. And that's the same for operation 2. Their key to produce, or their visual signal to produce, is an empty spot after them as they're feeding their customer and so forth. In this case, you'll notice that you've got operation 1, 2, 3, and 4. Operation 1 is working on one, and they have a unit that is already completed, ready for operation 2 to pick up. And then so forth down the line. Who should be working here? Well, operation 2 should be working. They should have already grabbed that because they've got an empty spot here. They should grab that unit and start working on it to replenish that, which will then be the signal for that person to complete theirs and put it in place. Operator 3 here should not be working on another unit until that unit has been consumed. A material Kanban is basically where you have information flow out of a process and going to another process. So in this case, operation 1 is going to supply material into these individual processes, but the empty spot there is an indication that operator 1 or operation 1 needs to produce and supply that material to its customer operation. Typically, though, there's many signals that you can use. We could go back and use an empty container that we just circulate back and forth. We could use a virtual signal like an email or a computer signal that's internal. We also can use cards, and the examples you're going to see in a moment are all based on using cards, 1 or 2 part cards. So you typically will have a card that is attached to the container itself, and it may have a duplicate that's detachable from that container. Several elements of the card. You know that it has the name of the part, has how that part's going to be produced. Is it a machining card or a purchase card? It has the part number. It has the quantity to order, 25. There's 25 in that Kanban, and there are 4 Kanban cards total. So the maximum inventory we'd ever have for these parts is 100. It's very unlikely you'd actually have all 100 at one time because of the lead time. You work out of one, you consume it, takes 2 weeks to get it replenished. And you keep working on the next one. When it gets exhausted, it's going to take 2 weeks for that to get replenished. So typically speaking, we have about half of the inventory in the Kanban system actually in process at any given point in time on average. You'll notice it also goes through 25. Is it each? Is it pounds? Is it liters? Is it feet? We'll have a Kanban purchaser card. Who's responsible for purchasing these? This is abbreviation or a code to indicate the individual purchaser. The person who's going to, if they're going to purchase it, who's going to actually go purchase it? If you're going to machine it, who's responsible for managing that within the machine cell? Lead time in weeks, the name of the component, and of course the Kanban rack. Now you'll notice in the MRP system, we typically have a mezzanine structure that is not dedicated. You can put parts anywhere in the mezzanine you want. That has its advantages and it has its disadvantages. A Kanban system, though, leverages the idea that we have a planned maximum amount of inventory we could ever have for that particular part, and then we dedicate a location in a mezzanine where we're going to keep that part. And you would have in this case, four slots for that inventory to be stored. And we would actually dedicate a specific card in a specific container to a specific place in the mezzanine. So we always know where the parts are and where they belong. Now, of course, this is a fluid thing and it's likely to change over time and may change very rapidly based on the fluctuation within your demand system and your production system. There's another type of Kanban here, and you'll notice they're taking these cards and they're putting it on the board, starting from right to left, or you could start from left to right. This is just one system that we have put in place. You have 3 different lines. That card is going to be placed on the board, starting from the right and moving to the left. You'll notice the size of the card is relevant to how long it's going to take to replenish and or how many parts are in that. But you put them on the board, and you'll notice at some point, if you get too many cards on the board, it's going to start inching into the yellow zone. And you keep getting cards, you're going to get into the red zone. That's an immediate signal you need to replenish that. So in this example, you notice the cards actually have different sizes. And this is indicating that they may have a different lead time or they may have a different order quantity. But those cards are put on the board. You notice C is a much bigger card than a B, which is a little bit smaller than an A. But as you move from right to left, when it gets in the yellow, that's danger. You need to go ahead and replenish those Bs. Or the Cs, you notice you only have 4 cards and you would be in the yellow. A's would have multiple cards to get in the yellow. But it's information flow. It's basically just telling you once you use the, and this would be multiple Kanban cards that are being hung. Once you get to a certain point, you're in the yellow and you continue to the red. But it's a signal of what to go to produce first. So in this case, they should produce Bs before they produce Cs because Bs are in the yellow. So when we look at material Kanbans, there's a supplier Kanban where information is sent back to the external supplier, a production Kanban where it's sent back to an internal supplier. And sometimes you have a withdrawal Kanban where you actually have information stored close to the customer until the supplier has a chance to retrieve it. You actually keep it there, and then the supplier will come along periodically and grab that demand and then take it back to their location and replenish it and return it to you. We could use cards, we can use visual signals. It could just be like an empty container that's being sent back, like a hard signal. Or it could be a flag that goes up and says, hey, I need extra one of these. It could just be an empty spot on the floor that says, hey, that pallet's been exhausted, get me another pallet. So we have to talk about the Kanban calculation. How does that calculation work, and how does it determine how many containers we need? So there's some things we have to take into consideration, and this is part of the discussion that we had when we went through demand variability. The supplier lead time, often that's taken directly out of our MRP system. We want to verify that it's correct, and then we have to make sure that we have a good average and a standard deviation. So the challenge we have with the MRP system, it'll usually say, what is just the average consumption in units per day, per week, per month, or whatever the period happens to be. But we need to know the standard deviation as well so that we can do a better job of predicting how much inventory we need to have in the Kanban. And that plays into the safety stock down at the bottom. The average usage is just the average number of units consumed during some time period, per day, per week, per month. Safety stock then is a calculated cushion to help buffer. It's a buffer to help accommodate variation in demand or supplier lead time or quality or whatever the case is. Typically, safety stock is your standard deviation times 3 times the square root of the lead time. And what that does is it calculates a specific amount. Now, if you use your inventory out of the Kanban at the given rate of units per day, units per week without a safety stock, and everything is perfectly maintained at a very consistent demand rate, then you won't run out of material either. But sometimes you get demand for 7 units, sometimes it's 9 units, sometimes it's 8 units, sometimes it's 13 units. The average may be 10, which means half the time it's below the average and half the time it's above the average, as we discussed when we talked about our normal distribution in 68, 95, 99, 7 rule. So the safety stock is just a cushion to help accommodate that variability. So the raw reorder quantity then typically is your lead time times your average period. So if you're looking at lead time in weeks, then you would take your lead time in weeks times your weekly average plus some safety stock. Now, there is a Kanban calculation worksheet that's provided in the files that I handed out at the beginning of class. You can refer to that, and it'll actually take us through how to do a calculation. This is an old one I set up. We did this, and I actually referred to the example previously about the laminations that were being purchased. And this is the actual lamination part number demand that we're looking at. Actually, I take that back. This is a commutator shaft demand. So we did this for multiple components within that particular process. In this case, you look at, they've got their average demand that goes through here, through some time period, per day, per week, per month, whatever that is. At the end, it calculates for us our lead time, the period average, the sub-period average. We had to monkey around with it because this is an old MRP system, and it would store the data into 13 4-week periods. We took that period and just assumed that it was equal demand during each week, which of course is a big assumption, but that's what we were compelled to do. We then calculated our standard deviation for that and calculated our safety stock. And then you'll notice we had different levels of 2-bin systems, 3-bin systems, or 4-bin systems. So I would suggest that you look at that particular file at your own leisure. It'll help explain how those Kanban systems were working and how the calculations were completed. Now, in this particular example, I've got some sample card flows and sample material flows, and I'll just talk you through those relatively quickly. This is 4 different procedures that we set up, and actually kind of fun. This is an older example, but I use it just because that's how I learned the whole system, and that's how I learned how Kanban works, and I've applied it numerous times since. But in this particular example, when we trained operators, we actually built miniature cards and miniature boards and miniature boxes that would move, on a tabletop to indicate or teach people how the system worked. So in this case, you'll notice there's 4 containers on the shelf. Each one has its reorder Kanban card hanging on a hook. Here's your super deluxe machine-o-matic, and here's your Kanban board. We'll refer to that in a moment. So at this point, we have a placard, and it tells us, use this box. Don't be using it out of the other box. This is a key point in the Kanban. You only work out of one box at a time. You can't work out, if you work out of multiple bins at a time, you're going to violate your rules, and you're going to wind up running out of material. So in this case, the placard says, use this as your point of use. So they're working and they're pulling parts out, and they're pulling parts out, pulling parts out, pulling parts out. Eventually that box is exhausted. They take that box and either discard it or send it back to the customer or do whatever they do with the box. They move the placard over to the next rack to say, hey, now we're not going to start working out of this box. They take the Kanban card and they actually go and they hang it. You'll notice 2 sections on the Kanban board, the to order and the on order. They exhaust that box, discard it, they move the placard again, they keep working on it, they hang the Kanban card. Once per period, usually once per day. Sometimes it's more frequently than that, but at least once per day. The material reorder person, right, purchaser in this case, would walk out on the floor, which was always a challenge. Purchasers like to sit in their office and, especially if they're used to MRP, they like to sit in their office and manage their MRP system. To get them to walk on the floor can be a challenge in some cases because people aren't accustomed to doing that. So in this case, we had to convince and really had to work with our purchasers to go out on the floor. But the idea is they make a round once a day minimum. It's better if they do it more frequently. But they'd walk out on the floor, they'd go to their Kanban card, they would see what's on a to-order system, and they had a sheet with all the parts they were responsible for purchasing, and they would just put tick marks on their sheet. They would also put a sticker on the Kanban card, and in this case, we would put the expected date of arrival. So basically, it would be our lead time from the date of the reorder, which would be today. So if it was a 2-week lead time, then it should arrive 2 weeks from today. And we would put that date on that little sticker and hang it on the board. Well, everybody keeps working. A few weeks later, the material arrives. we put the box on the shelf, we grab the card off the board, take the sticker off, re-hang it on it, and then we continue working until we get back around the system to that box. Here's a second procedure, very similar to the first, but we actually take the bin, and instead of pulling out of the bin while it's on the shelf, we actually take the bin and take it to our workplace. So in this case, they're working out of this box, working out of this box, working out of this box. When that box is consumed, we pull a box off the shelf, bring it, and start working out of that box. We take the card, we hang it on the Kanban card board, just as you saw a moment ago. Same thing, you exhaust the box, you discard the box, you hang the Kanban card, and you move the box to your work area and start working with that box. Again, the purchaser comes and notes what's going on. They reorder the cards, they hang the cards on the shelf, or they put the sticker on the shelf and they place them on order. When the material returns or arrives, they put the box on the shelf, they take the card, remove the sticker, put it on the shelf, and all is well. Another example where we're actually working out of a container, but we're picking more than one unit and storing it locally. So you may have a box of 1,000 here, and we pull out 100 at a time. Maybe there's 10 boxes of 100 each. We go grab one box, take it to our workplace, and we're working out of this box. We pull a whole box and we start working out of that periodically until such time as this original box was exhausted. Then, of course, you move the placard, you hang the Kanban card, and now you start pulling your material and storing it locally out of the second box. And we continue that until such time as the purchaser reorders, the parts come in, you put them on the shelf, you hang the Kanban card, take the sticker off, and all is well. Here's another example, and I referred earlier to to the way that I manage toilet paper. And I manage a lot of things in my home the same way. But when you're working out of if you remember the paper towel, I have a cabinet that will hold, it's in my laundry room, it actually will hold 12 rolls of paper towels. I buy rolls in packs of 9, and I just watch. When I get down to 3 paper towels left, that's my signal to buy more paper towels next time I grocery shop, which is typically once a week. I'll buy a bag, a set of 9. I'll put them back in that cabinet, and I'm filled back up to somewhere between 9 to 12 would be on the shelf. I never run out of paper towels because I'm constantly replenishing using that system. Well, this is the same way, and I've seen these with containers where you're pulling out of the bottom and things flow from the top. You see this in convenience stores where people pull a Coke out of a refrigerator. They open the door in a convenience store. They pull it from, and all the materials forced down through a spring and also through a little ramp so it can be replenished from the back. And they'll go in the cooler and replenish it from the back. But in this case, starting with a full rack of material, we will start pulling material off the rack, and once we go past a specific location, it may be half the quantity's been used, it may be a line on the table, we would take the card and we would hang it on the board to reorder material. That would be reordered. We're continuing to work out of that left-hand side, the right-hand side. Once the reorder material comes back in, we put it very carefully over to the left-hand side, and we keep working out of the right until such time as we exhaust all those boxes. Then we start working out of the left. But when we start working here, you'll note when this gets empty again, we'll rehang the card to order half the quantity. So those are just a few examples of Kanban systems that I've used in the past. There's a lot of other variations on that. But again, it's a signal system that tells upstream to produce material to replenish what's been pulled. So again, if you need to put it in a Kanban system, I'd suggest you do a little more research on your own, understand how those systems work. They can be very powerful replacements for MRP systems. Again, they're not a one-size-fits-all. They don't fit everything. They don't work in every situation. But in the situations where they do work, which is actually the majority of the time, they're very efficient and a very visual way to know if your system has the proper inventory, the proper materials to complete production, and to serve as a signal upstream to replenish material that's been consumed. Thank you.